Hello, in this class we will look at energy usage by humans, and in particular we will try to look at the impact that we have through our energy usage on the atmosphere. So, if you see popular discussion, you see articles in newspapers, magazines, you hear a lot of discussion on what we need to do with respect to global warming and so on. A lot of that discussion is based on this idea that something that we do is impacting the composition of the atmosphere. So, there is at least in the popular audience, there are some disagreements on the extent to which we make an impact on our atmosphere. So, what we are going to do today in this class is to basically go over a calculation, step by step calculation, where we will look at what is it that we are using and what kind of an impact that has on the atmosphere, and how seriously we need to consider it. So, this is the kind of thing that we will look over in this class. So, the learning objectives for this class are basically twofold. First of all is to our intention is to carry out a calculation based on the energy usage by humans. So, just that process, what is that process that we are going to go over to do this calculation is itself a sort of a learning objective for this class, so that you get a sense of how to go about this kind of a calculation. And also in that process I will also try to highlight the kinds of approximations we make and what assumptions we are making and so on. So, that is something that is I think of interest to look at. So, that is a learning objective for this class, so that we will do. And we would also like to estimate at the end of our calculation, to estimate the impact on the atmosphere that energy usage by humans has. Okay. So, that impact on the atmosphere that we are creating as a result of our usage of energy is also something that we would like to figure out, and is also a learning objective of this class. Okay. So, with these two ideas in mind, we will begin our discussion on this topic. So, I think we looked at this in another class, but I will just highlight a couple of points here. So, the first is that there are estimates on how much energy humans are using per year as of now. As of now, what is our annual energy usage, and that is a value that is 500 exajoules. Okay, so 500 exajoules. So, that is an exajoule is the prefix exa is given if you have 10 power 18 as the order of magnitude of that quantity. So, we basically have 500 into 10 power 18 joules being consumed every year. So, that is 500 into 10 power 18. So, 500 into 10 power 18 joules per year is what we are consuming. So, that is the number that we have to work with. That is a very important quantity that we need to keep in mind when we do this calculation. This image of course is courtesy of NASA. It is an image produced by NASA using several hundred, maybe about 400 images individually located, I mean gathered from around the world using their satellites, and then stitched together to create this image. It is a nighttime image which shows you how much of electricity is being used at various places, and gives you an idea of how the energy usage is distributed across the world. So, even as you look at this number, we also have to keep in mind that this is not uniform across the world, but regardless this is the energy that we are using as a species, and so that is the number that we need to work with. So, we will keep this number in mind, and we will proceed on that basis. So, to do our calculation, we have to have some starting points. So, the first starting point is to get a sense of what are the major constituents of dry air by volume. Okay. So, we would like to get a sense of what is the percentage of that constituent in the air, and that is something that if we have as a starting point, we can then compare what it is that we are doing and how much is it likely to change this composition. Okay. So, the source for this data is Wikipedia. So, that is the source. You can go ahead and look at this source. It gives you the same composition and of the various gases that are present in the atmosphere. So, if you look here, we have the most significant constituent is nitrogen. So, that is about 78% of the atmosphere by volume is nitrogen. The next major constituent is oxygen, and that is about nearly 21% is oxygen. So, these are the two major constituents of air, and that is what we are breathing in and out all the time. The other constituent which perhaps we do not talk about much at all is argon. that is 1% of nearly 1% of the atmosphere is argon, and then the fourth major constituent is CO2. So, I think these are the ones that we really need to look at, and particularly we are looking at CO2 because that is the one that we are generating whenever we are consuming energy, at least as of today. A large fraction of the energy that we use, in fact a very large fraction, we will see the correct kind of numbers in another class, but essentially as long as you are using any kind of a fossil fuel, you are using any kind of even if you are using electricity that has been generated using coal, then essentially you are releasing carbon dioxide into the atmosphere. So, CO2 is the ingredient that we need to keep an eye on, and today there is a lot of discussion about CO2 being a prime contributor to global warming. So, we got to have a idea of how much of CO2 are we putting into the atmosphere, and how much of a difference is it likely to make, and at what rate is it going to make, that is the difference. So, I will also point out that we are not including in this calculation the presence of water vapor. So, some of the things I will assume in this calculation as we do this calculation, just so that we can have some control on what numbers we are dealing with here, is that by and large I will assume all the other constituents are undisturbed by this calculation. We are only looking at CO2, and we are not really looking at the effect of any of these other gases being present there. We will just assume that they are all other inert or at least non-participating factors in this calculation. So, we will leave that there, and so there are some details with respect to moisture that are indicated here, and particularly you also need to keep in mind that this moisture is not constant, depending on whether you are at a desert kind of a location or you are at a sea coast, whether you are in winter kind of conditions or you are hot humid conditions somewhere closer to the equator. Based on these conditions, the humidity in the air can be dramatically different. So, we are not looking at that, we are not going to consider that as part of a calculation. So, we are just going to ignore that for the moment. We are simply going to look at the rest of the gases and particularly CO2, and in principle the calculation we are going to do is actually quite simple. We are simply going to take the total amount of energy that we are using per year and see how much of CO2 will be released into the atmosphere if all of this energy comes from a carbon based source. That is all the calculation we are going to look at. We are going to look at this total energy 500 exajoules of energy and see how much of CO2, let us say by per volume of CO2, how much of CO2 are we going to release into the atmosphere if we can get all of this energy using carbon based fuel. And just so we get an idea of how much of an impact it has, we are simply going to compare it against the amount of CO2 already present in the atmosphere, and we are just going to estimate approximately how many years or how long will it take for us to double the amount of CO2 in the atmosphere simply because of our use of energy. Okay. So, doubling the quantity of any gas in the atmosphere is a very significant impact on the atmosphere. We cannot look away that there is from that parameter. If we know that we are suddenly going to double the concentration of something in the atmosphere, and it is not just something inert, it is doing certain specific things in the atmosphere. It could be anything, it could be holding back the longer wavelength radiations, etc. Any number of things it could be doing out there which we may not have complete control on, and so if you are going to double that quantity of that particular gas, it is a reason for concern, or it is at least a moment for us to reflect on, and so that is all that we are going to do. We are going to see how much CO2 is going to come out and how long it will take to double that amount of CO2 present in the atmosphere, assuming we continue to use energy at this present rate. You should also keep in mind that typically over the years our energy usage has only been going up. So, what is 500 exajoules now, 10 years from now could be significantly different. Chances are it is going to be much higher. So, this calculation in that sense is even a conservative calculation because we are only looking at today's usage. Okay, while we do this calculation, we need to understand what part of the atmosphere are we dealing with. Okay, so the atmosphere is something that has many layers. People who spend a lot of time on atmospheric science have actually looked at the layers of the atmosphere and have put different strata of the atmosphere for which they have names. So, for example, the lowest level of the atmosphere is referred to as the troposphere. So, this is actually from somewhere between 0 and 12 kilometers from the the entire atmosphere, that is from the ground level to about 12 kilometers above the ground level is referred to as the troposphere. So, essentially a very large fraction of human activity is in this range. We are basically a very large fraction of our population is basically on the ground. All the stuff that we do, all the work that we do, all the machines that we run are typically on the ground. We also have a fair number of aeroplanes which are flying in the sky. Increasingly that is a significant number, significant enough that we are looking at pollution impact of those vehicles in the air. But if we basically are on a transatlantic flight, for example, the most of these flights level off at about 10 kilometers of height. So, typically they are at 10 kilometers of height and about 1000 kilometers per hour speed. So, 10 kilometers of height and 1000 kilometers per hour speed is roughly the kind of numbers that you are looking at when you are on a transatlantic flight. Next time you are in one of those flights, you have an opportunity to, or even a long distance flight, even within within your country, if it's long far enough that the flight reaches its optimal cruising altitude, you will find these are the kinds of numbers that that are on display if you have such a display on the flight in a display in front of you, or if the pilot announces it to you. So, just note for those, look out for those numbers, and those are the numbers you are likely to see. So, most of the jetliners, modern jetliners are flying around 10 kilometers altitude above the sea level, and so they are all flying in the troposphere. All the propeller planes, the turboprops are all flying much lower than that, and for the most part this is all that human activity is. It stays within the troposphere. Just to we do a little bit of things in higher altitudes as well, but so just for sake of completion we will briefly look at what's going on at the other layers. But for the most part our direct involvement there is a bit on the lower side. So, the next higher level is the stratosphere, which is 12 to 50 kilometers from the ground. So, it starts off where the troposphere ends and then continues up till about a 50 kilometer altitude, and the ozone layer, which is a very critical layer for us, is in this stratosphere. And so, that is really the main thing that is present in the stratosphere that is of interest to us. A few of the jetliners will get into the are in a position to get into the stratosphere, but for the most part our typical commercial flights are not really getting into the stratosphere. They tend to stay in the troposphere. So, that is in the 12 to 50 kilometer altitude above the sea level. Then we have the mesosphere, which is 50 to 80 kilometers up from the ground, and this is where in fact when you look up in the night sky and you see a meteor burning up, generally it is believed and estimated that this is the range of the atmosphere over which the meteors burn up. So, so that is where this mesosphere enters into our frame of reference, and where we even actually get to see it sort of indirectly when you look up into the sky and you see this meteor, a shooting star going through the sky, then it is something that is happening in the mesosphere. Above that is the thermosphere, which is starts off at about 80 kilometers above the ground level and then goes up to about 700 kilometers above the sea level. So, for us of interest in this thermosphere is the fact that let us say the International Space Station is situated somewhere in this range of distance from the ground. It is somewhere in the middle, in fact about 300-400 kilometers above the ground level is where the International Space Station is. Okay, so this is how the various layers of the atmosphere are with respect to what activities we do. Much outside this is the exosphere, which is finally what merges with the open space out there, and where solar wind then takes over. So, that is 700 to 10,000 kilometers, and beyond that the solar wind takes over, and you are basically looking at open space well outside the realm of the earth. So, these are the various layers of the atmosphere, and this is how they stack up. And for us of interest is this troposphere, which is 0 to 12 kilometer, and it is also of interest that for us to note that 80% of the mass of the Earth's atmosphere, 80% of the mass of the atmosphere, Earth's atmosphere, is in the troposphere. Okay, so 80% of the mass of the Earth's atmosphere is in the troposphere. Therefore, we will restrict our calculation to this 80%. We will restrict our calculation to the troposphere. Okay, so we are going to in any kind of a calculation of this nature, for us to do it in any reasonable framework of time, some number of approximations we need to make, and it is for us to see if those approximations are reasonable and that they are not far fetched, and also that we are not drastically changing the frame of reference of that system. So, for now we will make this approximation that troposphere is where all of the Earth's activity is largely taking place, and that since 80% of the atmosphere is there, let us just stay focused on it, let us not worry too much about, we will sort of assume that that is our atmosphere, that we are not really worried about the rest of the atmosphere, and then within this troposphere is what we are going to do this calculation. Okay. So, all the calculation we will restrict ourselves to this troposphere. So, again this is the source for the data, and you can also go and look it up. So, now let us estimate, now that we have said that we are actually going to work with the troposphere, let us estimate the volume of the troposphere, or rather we will basically estimate the amount of the volume corresponding to the gas that is held in the troposphere, alright. So, to do that let us look at a few simple numbers here. We have here the radius of the earth, which is 6,371 kilometers. Again some approximations you have to make. The earth is not a perfect sphere. So, but for the purpose of this calculation we will assume it is a perfect sphere. So, again these are approximations that are reasonable, and therefore, I think are just absolutely fine. So, if you simply do volume is four by 3 pi r cube, and we use this 6,371 kilometers as your r, value of radius of r, then we get this answer of 1.088 into 10 power 21 meter cube as the volume. This value that you see here, that is the value you will get as the volume of the earth. Okay. So, that is the volume of the earth. This volume is not immediately of importance to us. We are more interested in the volume of the atmosphere that is just above this earth. And so, if you simply look at as we just saw in our previous slide, that the troposphere goes from 0 to 12 kilometers height. So, we now need to look at a sphere where we use a value of r. So, for the value for earth we use r is 6371 kilometer, and for the earth plus the troposphere we look at a value of r which is 6383 kilometer. And then when you subtract the two, you subtract the volume of the larger sphere from the volume of the smaller sphere inside it, which is the volume of the earth, then you get the volume of the so 4 by 3 pi r earth cube, actually I should change this, earth plus troposphere, 4 by 3 pi r of earth plus troposphere cube, that is earth plus troposphere, and this is only earth, minus 4 by 3 pi r earth cube. Okay. So, if you do this, then you will get the value that you see above, which is 6.133 into 10 power 18 meter cube. So, this is then the volume of the troposphere. Okay. So, this is the volume of the troposphere. So, by just quickly looking up simple values, which is the radius of the earth and the thickness of the troposphere, and then calculating the volume of the earth plus the troposphere, and then subtracting from that the volume of just the earth, we get the volume of the troposphere. So, this is the volume of the troposphere, this value out here, 6.133 into 10 power 18 meter cube, that is the volume of the troposphere. Okay. So, you can run through these numbers and you should arrive at a value of this nature. The image that you see here is courtesy of ISRO, the Indian Space Research Organization. So, it is just an color image of the earth. You can in fact see, I believe that is India right here. Right here you will see you see India, and somewhere here is Australia, and I think somewhere here you should see edge of Africa showing up somewhere there. But anyway, so this is just the photograph of the earth, and more specifically I think what is of interest, I just put this image up to just highlight one aspect of our calculation, which actually was very nicely stated in some other discussion that I had heard earlier, which is basically that if you take a globe in your house, which let us say you have a sphere in your house which represents the earth, and you have the map of the earth plotted on that sphere, then if you see here, if you look at this value 6,371, and the fact that the 80% of the atmosphere is within 12 kilometers of this. Okay. So, that 12 kilometers is a very small dimension, small distance relative to the 6,371 kilometers. So, if you take a globe which is that size, then a coat of paint or varnish or whatever it is that you have put on the globe is really all there is in terms of the equivalent of the thickness of the atmosphere. So, the atmosphere is so thin relative to the the overall globe that we have. So, we think there is a big atmosphere above us, it is large relative to us, but if you take into account the size of the earth, it is really not that not that very large. It is a very thin layer, and that was a very nice description I saw elsewhere, where they refer to it as not being thicker than the coat of paint or coat of varnish that is present on a typical globe that you might buy commercially somewhere. So, anyway, so this is the value of the thickness, the volume of the troposphere, right. So, we will keep this number in mind, and let us now consider the fact that if you go back to the composition, of the air, dry air, then we find that 0.04% of this of the volume of the atmosphere is carbon dioxide. Okay. So, we will use the same 0.04% and say that 0.04% of the volume of the troposphere is the carbon dioxide available in the troposphere. So, if you come here, that is exactly what I have done. This is the volume of the troposphere, and if I take 6.133 into 10 power 18 and multiply that with 0.04 by 100, you will get this value here. Okay. So, so that is the volume of carbon dioxide present in our atmosphere. Alright. So, we have simply just looked at the percentage and come up with this calculation, and you can just again, as I said, run through these numbers and you should see some number close to this. So, that is any interesting now an interesting quantity for us to keep in mind. So, we are, as I said, by the time we complete this discussion, we are sort of also curious to figure out what are we doing with in comparison to this volume, and how quickly we may end up generating CO2 which matches this volume, which means we have now doubled the amount of CO2 in the atmosphere. So, that is something that is of significance, and we are trying to get a handle on, we are trying to get a feel for how long does it take for us to do something like this, alright. So, now we have now got this idea of how much carbon dioxide is present in the atmosphere. Now, I would like to look at the second part of this calculation, which is that we are using some amount of energy. How much carbon dioxide are we releasing as we use this amount of energy? So, that is the second part of the calculation we have to do. For this, again we have to make some assumptions. So, since we are now looking at carbon dioxide as the aspect that we are focusing on, we will assume that the energy is coming to us through the use of fossil fuels which are carbon based. Carbon based fossil fuels are being burnt to generate the energy that we are using as human beings, and so on that basis we will figure out how much carbon dioxide is being released. So, is this an unreasonable assumption is the first question we have to ask ourselves. So, actually it turns out that it is a very reasonable assumption, because if in today's world as of as we approach the year 2020, if you look at what is the source for a vast fraction of the energy that we are using, the source for vast fraction of the energy we are using is coal. Coal is what is being used in many places to fire up the power plants, and through that only we are getting our electricity. So, while we sit at home and we use electricity, or we sit in our office and use electricity, the source of the electricity is often based on coal. Increasingly there are countries which are looking at other renewable sources of energy, which is what we will see as we go through with our class. But today if you just look at the scenario of how much energy is being generated using a carbon based source, a very large fraction of the energy is being generated by the carbon based source. And so, for all the energy that we use, the 500 exajoules of energy that we use, a significant fraction of that has come from coal, and so for the purpose of our calculation we are just going to assume that all of it has come from coal. Okay. So, that final approximation we are making just for the purpose of our calculation, just to get a sense of what we are doing with respect to it, and that is not a very unreasonable assumption, it is a fairly reasonable assumption, and we will see that in one of our later classes. So, let us now look at the composition of crude oil, for example. Again you take some hydrocarbon based source which typically comes from crude oil, and then you are going to use it to generate energy. So, if you actually see a significant fraction of the crude oil is carbon, is based on has carbon as its main element which is present in the crude oil. Again, this is the source for this data, you can again look it up on your own as well. So, about 83 to 85% of what is present in crude oil, which is being taken off of the ground at so many places is carbon. I will also point out that the exact composition of crude oil varies from location to location. So, this is only some kind of an approximation of the composition of the crude oil, but generally it is in this range, and therefore, it is an acceptable number to go with. So, you do have carbon, you have hydrogen, you have nitrogen, oxygen, sulfur, even a very tiny amount of metal that is present in the crude oil, but large fraction, this 83 to 85 is carbon. And so, for our purposes, this is all we are going to focus on. We are just going to focus on carbon. We are just going to say that, in fact, technically you can even be burning hydrogen. 10 to 14% is hydrogen, and that also is going to burn, generate water, and generate some energy. For the moment, we are ignoring it. So, we are just basically looking at the carbon as the source. So, we may be off by about 10% in our calculation, 10-15% in our calculation, but that is not a big issue given the kind of numbers that we are dealing with. So, that is the point that I wish to make. Keeping this in mind, let us move to the next part of our calculation, which is basically to look at the heat of formation of carbon dioxide. Okay. So, how do you look at what is the energy that you are getting from some fuel, any fuel? You have some fuel that has some components in it, they all get oxidized, and that is how you release energy. So, how do you know what is that energy? So, people have done careful studies on these, and you have tables for these, thermodynamic tables are available, and they are in a position where you can go and look up the heat of formation of a compound. Okay. So, heat of formation of CO2 starting from carbon, which is in graphite form, and then it reacts with oxygen and generates CO2 for you, and in that case how much energy is it releasing, right. So, you will see a number of this nature, minus 394 kilojoules per mole is the typical number that you will see. So, why is it minus? It is minus because that is the sign convention that is used. It means that heat is leaving the reaction, that is, it is an exothermic reaction, right. So, if it is an exothermic reaction, they put a minus sign in front of it, and so this is an exothermic reaction, and that is exactly why we use it as fuel. We use it as fuel because this is the amount of energy it is releasing, and then we are able to use that energy for a variety of different things. So, this is the amount in kilojoules. So, 394 kilojoules per mole of the carbon dioxide that is generated. So, a mole in this case, if you take carbon, 1 mole is 12 grams. So, every time you burn 12 grams of carbon, this is you will get some corresponding amount of CO2. So, you will get what 12 plus 32. So, you will get about 44 grams of CO2, but basically you will release this amount of heat for that when you do that combustion process. Now, 1 mole of CO2 corresponds to 22.4 liters at STP. Remember that this is STP, or in other words, if you want, since other calculations we have done are in meter cube, the volume of the troposphere that we calculated was in meter cube. I will simply convert this liters into meter cube. 1 liter is 10 power minus 3 meter cube. So, 22.4 liters is 22.4 into 10 power minus 3 meter cube. Okay. So, that many meter cube is what 1 mole of carbon dioxide will correspond to at STP. Now, STP is defined as 0 degrees C and 1 atmosphere pressure. Actually, 1 atmosphere is now a little bit of an approximation. But in any case, we can assume that to be the correct definition as of now. It is 0 degrees C and 1 atmosphere pressure. That is a pretty good number to go with, set of conditions to go with. So, that under those conditions at 0 degrees centigrade and 1 atmosphere of our atmospheric pressure, 1 mole of carbon dioxide will occupy 22.4 into 10 power minus 3 meter cube, or 22.4 liters. Now, you can ask yourself, the entire country is not sitting at 0 degrees C. If you take India for example, it is definitely not sitting at 0 degrees C for the most part, maybe a few places up north. If you cross Delhi and start going further north, as you get into the winter seasons, temperatures can drop to 0 degrees C, can go below 0 degrees C. There are places in the world which are sitting which are well below freezing conditions, where there is a lot of snow. So, they are definitely below 0 degrees C, and more importantly, that is just the surface of the earth. if you start climbing up from the surface of the earth, as you go to higher and higher altitude, the temperature above outside the temperature at those altitudes keeps getting lower and lower and lower. Certainly this is so in the troposphere. So that is why when you are in a flight, if you are flying in a aeroplane somewhere high up in the sky, you will often have halfway into the flight the pilot will come on and give you some idea of where your destination is, how far you are from the destination, and usually they will also give you some idea of what is the speed they are traveling with and the temperature that is outside. Invariably you will find the temperatures that they will be referring to will be well below 0 degrees centigrade, that they will say temperature outside is such and such temperature. So the point is the temperatures that we are dealing with in the troposphere start off in the surface at various locations on the surface of earth at several tens of degrees centigrade, and as you go up into the higher ends of the troposphere, you have a temperature which is in the several tens of degrees in the below 0 degrees. So say minus 20, minus 30, minus 40 degrees C, and on the plus side you will have plus 10, plus 20, plus 30 kind of degrees C as the range of temperatures. So say minus 40 to say plus 30 is the kind of range of temperatures that you are looking at for the atmosphere, the troposphere across various locations. So given that this is the range, we just take 0 degree C as somewhere in the middle, and then we will assume that that is representative of this entire troposphere. So again there is an approximation there, and we will assume that this approximation is valid. So that is the way we are going to go about it. So therefore, so if you actually have completely different conditions of temperature and pressure, this number that we are talking of 22.4 will not be actually correct, but we are just assuming that this number is representative. The conditions we are of 0 degree C and 1 atmosphere pressure are representative of the circumstances that we have. Atmospheric pressure in fact is going to decrease as you go up, but regardless we will assume that this is the number that we are dealing with. So again an approximation for you to keep in mind. So given that we have this information, let us look at what we are dealing with. As I said, we have 5 into 10 power 20 joules of energy that we are consuming per year, alright. So if you go back here, the heat that is being released when you burn 1 gram of carbon, or you release 1 mole of CO2, in the process of releasing a mole of CO2, the amount of energy that is being released is 394 kilojoules, or 3.94 into 10 power 5 joules per mole. So if you take the total energy that is required and divide it by the amount of energy that is released, the total energy that is required here, and you divide that using the amount of energy that is released per mole of CO2 that is released, between these two you will get the total number of moles of CO2 that is being released into the atmosphere, right. You will get the total number of moles of CO2 that is released into the atmosphere as a result of the total energy that we are demanding from the system and the energy being released per mole of CO2, and every mole of CO2 occupies 22.4 into 10 power minus 3 meter cube. Therefore, if you do this calculation, we will get the total volume of CO2 being released to meet this energy requirement, to meet the yearly energy requirement. Okay. So this is the total volume of CO2 that is being released to meet the annual energy requirement of the human beings. So for all of us put together, this is the total volume of CO2 that is being released. So that is this number that you see here, 2.843 into 10 power 13 meter cube of CO2 is being released or will need to be released if the entire 500 exajoules of energy that is being used by mankind is released by combusting carbon. Okay. So that is the number now we have arrived at. So we have now gone through a calculation where we have made a bunch of approximations. We have assumed that the earth is spherical, we have assumed that all the atmosphere is only that which is within the troposphere. We have assumed that the conditions STP will hold for this entire set of this thickness of atmosphere, and also that we have assumed that all the energy is now being released from carbon combustion. So, if we do that, we come up with this number of 2.843 into 10 power 13 meter cube of CO2 that is going to be released per year to meet our energy requirements. So, now it is of interest to compare this number with the amount of CO2 that is actually already present in the atmosphere. So, let us do that. So, the total amount of CO2 that is present in the atmosphere is this number that you see here in meter cube. Okay. So, that is the volume of CO2 present in the atmosphere in meter cube, and that is simply the 0.04% of the volume of the troposphere. Okay. So, that is just 0.04% of the volume of the troposphere, and that is the amount of CO2 that is present in the atmosphere as of now. The denominator is the rate at which we are releasing CO2 based on our annual energy requirement. Okay. So, based on our annual energy requirement, this is the amount of CO2 we will release into the atmosphere every year. So, if you compare these two numbers, if you take the total amount of CO2 present in the atmosphere and divide that using this amount of CO2 that we are releasing every year into the atmosphere, we get a number of 86 years. So, in the present rate of usage of energy, if all of the energy is being released using carbon based sources, in 86 years we will double the amount of CO2 present in the atmosphere. Okay. So, that is a phenomenal increase in the amount of CO2. Please keep in mind that our planet has been, our solar system has been around for a few billion years, and we have had evolution occurring over several millions or tens of millions of years. Human beings have been around for several tens of thousands of years in various states of evolution, and if you take all of that into context, 86 years is nothing. 86 years just disappears. 86 years is virtually a fraction of a second of existence in terms of the entire evolution that has happened in humankind, right, on the planet, of which we have ourselves been in a very large significant period of time. Relatively, in the grand scheme of things, even our presence is not a very large fraction of time, but even with respect to our existence alone, 86 years is nothing. It's well within most of us these days. If you look at the lifespans of people around the world, at least in the say developed countries, or or at least in countries where there is better medical facilities, better health conditions, many people are living to be 80, 90 years old, right. So, within the lifetime of a single human being, you are doubling the amount of carbon dioxide present in the atmosphere. As a species we are doing this. Okay. So, that is a phenomenal thing that phenomenal way in which we seem to be interfering with what is some kind of an equilibrium that has evolved over millions of years of evolution in the atmosphere, right. So, a lot of things are happening in the atmosphere. CO2 is being released from various sources, and the plants are capturing the CO2 and then refreshing the atmosphere, etc. So, when we do something which is outside this scope of operation and suddenly start increasing the amount of CO2 present in the atmosphere, we cannot assume that the atmosphere will somehow take care of it. It does not happen that way. We have to have some way of handling this. At the moment we have not really consciously looked at it, but when we look at a number like this and we see that within a matter of 86 years we are actually going to double the amount of CO2 present in the atmosphere, it is definitely a cause for concern. We cannot just look the other way, we cannot pretend that this is a non-issue. We have to at least make a good attempt to understand what is the significance of having double the amount of CO2 in the atmosphere. Okay. So, a lot of people link this to global warming. A lot of scientific reports link the amount of carbon dioxide present in the atmosphere directly to the temperatures that are present in the that are being experienced across the earth, and therefore, if you double the amount of CO2, you are bound to have a significant impact on the temperature profile of the planet, and so it is not something that you can ignore. Also remember one other approximation which we made, which I said at that point, I highlighted at that point is a conservative estimate, is the fact that I am using today's energy usage, which is 500 exajoules per year, and this is something that has only been increasing. Okay. So, what is 500 exajoules here per year today? Maybe 10 years from now, maybe double in terms, because our population is only increasing. Even if our population levels off at some point, the amount of development that is happening across the population is increasing. Legitimately we want more and more people to have better quality of life. Generally better quality of life means they are going to use more gadgets, they are going to have houses that are better equipped, consume more electricity, consume more energy. That is the general trend. I mean, unless and until we can think of some better way of enabling higher quality of life without correspondingly increasing the amount of energy usage across everybody, including the people who already have this facility. Until and unless we figure something like that out, as of today the path is that for development to occur, more energy usage will be there. Most people will consume more energy, and therefore given that you could see even right in the very first slide that I showed you, where you saw energy usage across the world, there are significant fractions of the world which are still not using anywhere close to the amount of energy that the so called developed regions of the world are using. Naturally, when the rest of the world also starts using the same amount of energy as the developed world, the amount of energy that we will use in the world goes up significantly. So going up by a factor of 2 or factor of 3 is not at all impossible, even in the just extrapolating what we are doing right now. Okay, so going up by a factor of 2 or factor of 3 is not at all impossible. Please keep in mind, if our energy usage goes up by a factor of 2 or factor of 3, this 86 years will come down by a factor of 2 or factor of 3. So suddenly you are looking at 43 years, or you are looking at something even less, you are looking at something like say 29 years. So imagine this, instead of doubling the amount of carbon dioxide in 86 years, you could suddenly start doubling the amount of carbon dioxide in 49 years. You could double the amount of carbon dioxide in 29 years, and that is alarming. 29 years is nothing. By the time your son or daughter, if you have a son or daughter who is just born, by the time they reach they just complete their college, they are and start going into their first job, they are at 29 years or something of that nature, 25 plus years of age. And so even in that short time frame, if you suddenly double the amount of CO2 in the atmosphere, and if that has a major impact on the temperatures across the world, that is something that we need to be concerned about. We cannot just look the other way. I mean, it is quite irresponsible for us to just look the other way if that is the rate at which we are making a difference to the atmosphere. Please also keep in mind, a lot of people have opinions on this, and you can certainly look up a lot of scientific literature on this. Generally, the scientific community is convinced that having more CO2 in the atmosphere results in global warming, and when you have global warming, it leads to extremes in environment. It does not necessarily mean the whole place becomes hot. It generally seems to result in extremes in environment. So you have snowstorms that are very severe, you have cyclones that are very severe, you have droughts that are very severe. So each of these weather phenomena tend to become more severe. So and therefore the ability of the population to deal with it becomes harder and harder. They have greater hardship in dealing with this population, with this extremities in atmospheric conditions. So in conclusion, we can see through our calculations that first of all the fact that energy usage by humans can significantly impact the composition of the atmosphere. So I think that itself is a very important conclusion to focus our thoughts on, because there is at least I mean, in the popular perception there is at least some number of people have this idea that the atmosphere is huge, and there is no way that a bunch of us sitting on the ground can actually make a difference to the atmosphere, and therefore this whole idea of global warming, or that the amount of carbon dioxide in the atmosphere being high, etc., is all not really true, is the kind of idea that some number of people have. But we have just gone through a basic calculation, looking at some of the basic parameters that are involved in this process, of course making some approximations, which at each stage I try to explain to you what are the approximations we are making, and based on this we can understand that we are easily doing things that is changing the composition of the atmosphere significantly in a small time frame, not a very large time frame. In the grand scheme of things, as I told you, it's a fraction of a second in the grand scheme of evolution that we are changing the composition of the atmosphere. Naturally, that is not something that is likely to be a safe thing to do. And the fact that this impact on the atmosphere can occur in a relatively short period of time, this is exactly what I was just mentioning. The time frame is very short, that this is just a momentary thing in the grand scheme of evolution that we are making this difference. Please keep in mind many approximations we made. I will also add one more word of caution here. I spoke about how our energy usage is just going up, and therefore going up by a factor or 2 or 3 in energy usage is not so far fetched, which means this 86 years is going to come down by a factor of 2 or factor of 3. There is one other parameter that we are ignoring here, which is actually making this calculation I would say on the little bit on the relaxed side, it may be actually more severe than this, and that is how we are treating our forests. We depend entirely on our forests to fix the CO2, right. As of now, we do not, people are looking at new technologies to capture the CO2, etc. That is a different issue, and we have to see how far that can go. As of now, we are depending on nature, we are depending on the trees and plants and vegetation around us to help us capture the CO2, and uniformly across the world you will see that forests are being cut down. People have become very alert to it, and a lot of people have stepped up saying you cannot cut down forests, cannot cut down trees, and so there are significant movements around the world to protect our environment, to protect the forests, because that is all we have to protect the atmosphere that we have to live with. So that is a movement that is definitely there, but despite that movement, if you just see the general trend, you will see that because there is an industry associated with wood or with the need for firewood, etc., for a wide range of reasons, in general, at least in the last several years, forests have been massively cut down. So we are actually affecting ourselves, we are basically suffocating ourselves on two fronts. A, we are using so much energy with the only source or primary source being carbon, and so we are putting more carbon dioxide into the atmosphere. And B, we are taking away that one thing that the nature has, which helps us protect ourselves from this carbon dioxide, which is the plants. We are just cutting them down indiscriminately, and naturally we are only worsening the situation for us. So when I come to a calculation which arrives at 86 years, you can see that that itself is a number that is on the I would say on the larger side. Chances are we are working with numbers that are actually much shorter. So in summary, this is a calculation. In this class we have gone through a calculation which tells us what is it that what is the status in the atmosphere with respect to carbon dioxide, what is it that we are doing with respect to our energy usage, how does that impact the atmosphere, and throughout this calculation I have shown you, tried to alert you to all the approximations that are there, primarily because if you are interested, you can take up this calculation in much greater detail, or you can look at literature where they may have perhaps done this in much greater detail, where perhaps they make much better estimates of specific quantities and then go about the calculation. However, this calculation we have done is still reasonably good to give us an order of magnitude estimate of what we are dealing with, and that number as we came up with was well under 100 years, and therefore is something that we should be interested in looking at and interested in reflecting on. As we go through this course, we will look at a lot of renewable energy technologies, basic idea being that we can move away from this carbon based energy source and see if we can use other sources where we can meet our energy requirements without doing this impact on this negative impact on the atmosphere. Okay. So we would then have those technologies leading us to a path of good comfort with good environmental impact, and therefore a positive way to go about our existence. So we will see that in our subsequent classes. Thank you.